All right, so we're looking at damped motion now, and here's our example that we're going to work through. A 4-foot spring measures 8 feet long after an object weighing 8 pounds is attached to it. The medium through which the object moves offers a damping force numerically equal to root 2 times the instantaneous velocity. That root 2 is going to be the beta that we talked about. That's our damping coefficient, or our damping constant. Find the equation of motion if the object is initially released from the equilibrium position with a downward velocity of 5 feet per second. Find the time at which the object obtains extreme displacement from the equilibrium position. What is the position of the object in this instant? Okay, so as before in the previous example that we looked at, we are dealing with objects that are being measured in imperial units, feet, pounds, things like that, and we need to be working with mass instead of weight. So the first thing we're going to do is use that same relationship that we talked about before. Mass is equal to weight over acceleration due to gravity, g, which in this case, our weight is 8 pounds. Remember, g is equal to 32. So this is 1/4 of a slug. Okay? Next up, from Hooke's law, and we did this in the previous example as well, we know that K, our spring constant, is equal to W over S. Now, what is S here? S is the amount that the spring was elongated by. We're talking about a 4-foot spring that becomes 8 feet after the object is attached to it. So that means the displacement is the elongated spring minus its natural length, which would be 4 feet. Okay? So this is equal to weight, which is 8, divided by S, which is 4. That's equal to 2 pounds per foot. Okay? So this should be feeling a lot like what we did previously. Now, beta, remember, is given to us directly in the problem. Beta is what we're multiplying our velocity by to account for our damping force. And we're told that root 2 times the instantaneous velocity gives us that damping force. So that would imply that beta is equal to root 2 here. Okay? So that gives us the following dE. We have the second derivative of x dt plus beta over m. So that's root 2 over 1/4 dx dt plus k over m, 2 over 1/4 x equals 0. That's the equation that we came up with when we derived this damped free motion stuff. So simplifying that down a little bit, we're going to have our second derivative plus, this is the same thing as 4 root 2 dx dt, and plus 8x equals 0. Okay, now our solution, our equation of motion that we're looking for, requires us to use that value lambda and omega squared. Remember, omega squared is this guy. 2 lambda is this guy. 2 times lambda equals this, which means lambda would be half of that, 2 root 2. Okay? So from there, we get our solution. Now, what I need to do is look at lambda squared minus omega squared. Because remember, that's the discriminant that gives us those 3 different cases. So lambda squared minus omega squared, whether it's positive, negative, or 0. That's going to tell us which case we're looking at. Lambda squared minus omega squared would equal, well, lambda squared is 2 root 2 squared. Omega squared is 8. Not 8 squared. Remember, it's already omega squared as written, right? 2 root 2 squared is equal to 8, so this is 8 minus 8, or 0. We're looking at case 2 now. So that tells me exactly what my equation, or my solution, should look like. X of t is going to be equal to e to the negative lambda, so e to the negative 2 root 2 t, times c1 plus c2t. That's what we saw in case 2. Okay? We have initial conditions associated with this as well. So it says Find the equation of motion of the object is initially released from the equilibrium position. So released from equilibrium means x of 0 equals 0 with a downward velocity of 5 feet per second. Downward, remember, is the positive direction. So that means x prime of 0 equals 5. As before, if I want to use that that second initial condition, I need to know what x prime of t looks like. So this requires the product rule, negative 2 root 2 e to the negative 2 root 2t times c1 plus c2t plus c2 e to the negative 2 root 2t. Okay? All right, so let's take a look at our initial conditions. What does the first one imply? X of 0 equals 0 implies that 0 is equal to what? If I plug a 0 into this guy, the stuff in parentheses just becomes C1, and this guy out here, e to the 0, is equal to 1. So that just becomes 0 equals C1. What about x prime of 0 equals 5? What does that tell me? Okay, well, 5 is equal to, so let's plug in a 0 here. I'm going to get negative 2 root 2 times 1 times, let's see, plugging a 0 in is going to make this go to C1, so times C1. And then here, plus C2 times, well, this will be equal to 1 as well, so plus C2. However, we know what C1 is equal to. C1 we solved for already. It's equal to 0, which makes that term go away and just give me C2. So 5 is equal to C2. That means my equation of motion is this, e to the negative 2 root 2 t times C1, which is 0, times C2t. That's times 5t. I kind of like to put that in this form, though. 5t e to the negative 2 root 2t. It looks better that way. Okay? All right, so that's not the only thing that we were asked to do. We're also asked, it says, find the time at which the object obtains extreme displacement from the equilibrium position, and what is the position of the object in that instant. So extreme displacement means we're trying to maximize our position, right? We're trying to find the absolute furthest we get, maximize or minimize, really, the absolute furthest we get from equilibrium. And this is like a calculus 1 type of problem. We want to optimize x of t, so we look for critical numbers. Okay? Remember, this is what x prime of t was equal to. Let's use what we have for C1 and C2. I could also just take the derivative of this explicitly, or I can use what I already have. So if I plug in C1 equals 0 and C2 equals 5, then what I get here is, let's see, this guy becomes 5t times that, so that's negative 5 times 2 root 2, that's negative 10 root 2 e to the negative 2 root 2 plus C2 is equal to 5. Again, 5e to the negative 2 root 2 t there. Okay, that's equal to x prime of 0, or of t, not 0. X prime of t is equal to, let's simplify that. I could pull a 5e to the negative 2 root 2 t out, and this becomes negative 2 root 2 plus 1, okay? And we want to set that equal to 0. X prime of t equals 0 implies that, well, looking at this first factor here will never equal 0. It's an exponential function, so that means this is equal to 0. 0 equals negative 2 root 2 plus 1, which implies that, am I missing a t in there? I was supposed to put a t in there somewhere, wasn't I? Yeah, I'm missing a t right here. Yep, I forgot to put that t in there. So put that t in there. This implies that t is equal to 1 over 2 root 2. Okay? So that would be the time, that's measured in seconds, at which our displacement is maximized. We reach that extreme displacement. To figure out what the position of the object is in that instant, we just plug that right back into x. So I'm going to go like that. X of 1 over 2 root 2. That I would just put into a calculator because you have x already given to us explicitly. This one comes out to approximately 0.6503 once you do that. And this is measured in feet. Its position. Okay. All right. Very good. So let's go ahead and move on now. Feels like there's 2 pages there. Yep. There we go. Okay. Did I get these mixed up? No. So we're looking at another example here. After a mass weighing 10 pounds is attached to a 5-foot spring, the spring measures 7 feet. The mass is removed and replaced with another mass that weighs 8 pounds. The entire system is placed in a medium that offers a damping force numerically equal to the instantaneous velocity. The equation of motion, if the object is initially released from a point half a foot below the equilibrium position with a find that equation of motion if the object is released from a point half a foot below the equilibrium position with a downward velocity of 1 foot per second. Okay, so in order to do this, we're kind of starting out the same way. We're using a lot of the same stuff. So the mass weighs 10 pounds. We still need to find mass as opposed to weight. So what's that going to look like here? Our mass is equal to our weight over force due to gravity, which in this case is 10 over 32, or 5/16 slug. Okay? Now, the point of using the... Actually, I'm going to back this up a second. So I'm not going to end up needing this mass. I found it, but the reason if you look at the description of the problem, that weight is eventually removed and replaced with a lighter one. And the point at which we're going to need to use m in our equation isn't going to come into play until we use this. So actually, I'm going to line that out. We don't need that yet. The point of this is to find k, the spring constant, because the spring constant is going to be the same regardless of what mass you hang on it. So let's actually do that. In order to find the spring constant, we first need to know what s is. After hanging this 10-pound weight on our spring, it takes the 5-foot spring and stretches it into a 7-foot spring. That means that s, the elongation amount, is 7 minus 5, which is equal to 2 feet. Okay? Now we can use k equals w over s, which is 10 over 2, or 5 pounds per feet. So we need k. And now that we've found k, that first weight has served its purpose. It gets removed, and we put a new mass on the spring, which now weighs 8 pounds. I want that to be converted into mass. So mass equals w over g, which equals 8 over 32 now, which is the same thing as a quarter slug. Okay? So now this is starting to look a little bit more like what we want. Okay? All right, so let's see. Now what we want to do is use the information that we have here to set up our differential equation. So I'm going to do this a little bit differently than how I did it before. I'm going to label things as 2 lambda and omega squared first. So 2 lambda in this case is equal to beta over m. Beta over m, I didn't write down what beta was. I'll do that here. So beta is given to us in this sentence. The entire system is placed in a medium that offers a damping force numerically equal to instantaneous velocity. That's up here. If it's equal to instantaneous velocity, I could also say it's equal to 1 times the instantaneous velocity. And that 1 gives me beta. Okay, so beta is equal to 1 in this case. Beta over m is 1 over 1/4, or 4. Okay? Omega squared equals k over m. That's 5 over 1/4, which is equal to 20. Okay, so these quantities are going to be used in my differential equation. That means I have x of t equals second derivative of x with respect to t plus 2 lambda, which is 4, dx dt, plus omega squared, which is 20, x equals 0. And we also have some initial conditions to consider here. We're told that the equation of motion, we're looking for the equation of motion if the object is released from a point 1 foot below equilibrium. That would be in the positive part of our axis, so x of 0 is equal to 1/2 now. With a downward velocity, that's a positive direction, of 1 foot per second. So x prime of 0 equals 1. Okay? We can solve this guy and figure out which case we're talking about by looking at lambda squared minus omega squared. Okay? What does that equal to? Well, if 2 lambda equals 4, that means lambda is equal to 2, so that's 2 squared, minus omega squared, which is 20. That equals negative 16. A negative number means we're looking at case 3. Okay? Case 3 gives us the following solution. Oops. I just realized I did something kind of dumb here. I said x of t equals that. I shouldn't have said that. This is just the differential equation. This is where I want x of t. X of t in this case, based on what we saw for case 3, is going to look like e to the negative lambda, that's negative 2, t, times c1 cosine of omega t. So in this case, omega, or I'm sorry, not omega t. I'm thinking of the undamped version. Where's my page where I show this? Looking at my cases here. Case 3. Okay, look at the argument. It's the square root of omega squared minus lambda squared. So that'd be 20 minus 4, which is 16. C1 cosine of... and then that's... we went with the square root of that, so that would actually be 4t, plus C2 sine of 4t. Good. All right. And now, in order to use my initial conditions, I need to know the derivative of that as well. X prime of t. If you find x prime of t and then simplify, I'm going to jump to the simplified version to save some time and space here. E to the negative 2t times negative 2c1 plus 4c2 cosine of 4t plus negative 4c1 minus 2c2 sine of 4t. Okay? I worked that out ahead of time. You can verify that if you want. So now let's use our initial conditions to find our parameters. X of 0 equals 1/2 implies that 1/2 is equal to what? So let's look at our function. Plugging a 0 in up here will give me a 1 there, a 0 here, and a C1 times 1 right here. The whole thing becomes C1. So I have C1. X prime of 0 equals 1. That was our next initial condition. What does that tell me? Well, again, looking at x prime down here, if t is 0, this factor goes to 1. Sine of 0 is equal to 0, so we lose that whole thing. Cosine of 0 equals 1, and so I just get this guy. 1 is equal to negative 2c1 plus 4c2. Now I know what c1 is equal to. It's equal to 1/2, so I could plug that in here, making this a negative 1, add that over to get a 2. 2 divided by 4 is 1/2, so I get c2 equals 1/2. Both parameters are equal to each other. Okay, so that tells me that my solution is x of t equals, now since c1 and c2 are both equal to 1/2, I can factor that 1/2 out and just call this e to the negative 2t over 2 times cosine of 4t plus sine of 4t. Okay, so that gives me my position, or my function. Okay, and let's see, how much time do I have? I think I'll make one more video to finish this section up, so I'm going to stop this one here.